Welcome to the final exam, question number 20, and it gives us which of the following factors affects the shear capacity of a reinforced concrete beam. Alright, so let's assume you have a little pad. Here's your concrete beam. Obviously it's not the best, but let's say you have a pad over here. It's a simple concrete beam. And it's asking what affects the shear capacity of a reinforced concrete beam. So what you're going to have for shear capacity, before I even look at the possible answers, I'm going to say what helps with your shear capacity is your shear reinforcing. You usually have a lot of the more shear over here where your shear is high, the end. And then it'll go to say no, you don't know, or you might not know, 8 inches. And then it goes to, could be 12 inches, and then maybe 21 inches. And in other words, or 18. It has a region in this end area that's pretty darn high, and then it gets in the middle, where typically you'll see a beam moment. That's your shear diagram. It'll look like that, where you see in the middle. That's a horrible shear diagram, but hoping you get my gist. Shear is high at the ends and zero effectively if it's a uniform distributed load, zero in the middle. So that is why it is what it is. Now let's move on to the actual question at hand, and we'll go ahead and do what we normally do, cross out the ones that we know are wrong and see what we got left. Alright, which of the, and we're talking about shear capacity. Alright, and it says A, the ultimate 28-day strength of the concrete. And yes, that will affect that's, effectually it's F prime C. Does that affect the strength of the concrete? Does that affect the shear capacity? And I say yes, it does. So that's a yes. Let's look at the rest. Just make sure that there's not a better answer out there. And B is the grade, size, and spacing of the longitudinal tension. So it's saying the tensile. And no, that's a no. That does not. In real life, yeah, a little bit, but not in design. You don't design for that small bit of reinforcing steel in shear. So that's a no. C, the size of aggregate used in the concrete mix. And that is a no. The span length of the beam. The shear capacity. The span length of the beam. And this could be a trick. I mean, once you look at that, you could say, well, sure. The length of the beam is going to affect how much shear you have. The longer the beam, I mean, it should have more shear, right? You have more load. For instance, if you have a distributed load, distributed load is typically, WL over 2 equals V for a distributed load. So, yeah, well, sure, the L is going to double up. I mean, if you double length, you're going to have double the shear. But when you look at it, it says shear capacity. And when you're looking at capacity, that's going to increase your shear load. This is load, not capacity. So that's the length of this beam has nothing to do with your shear capacity. And just as it really has nothing to do with your moment capacity either. You could have an extremely long beam. Your moment capacity is going to be the same. The problem is your actual load is going to be, a heck of a lot more. So, especially when you start going the moment, you can, as you can see here, if it's uniform, if you double the load, you're going to double the shear. And moment, if you have a uniform load, obviously, and that's what most people, if you're just getting into structural analysis and engineering, you'll see this equation a lot, which is the max. What this truly is the max moment, which is always going to be in the middle of a uniform distributed load. So don't think that the moment is always going to be max. If you don't remember exactly if it was a uniform distributed load, maybe you have a point load, remember to do your shear moment diagrams, and you can once again derive this. Go ahead and do a shear moment diagram, and then throw this equation in there and say, oh, okay, yeah, it is for a uniform distributed load, and you'll have to justify this, or just memorize it, I guess. I justified this to myself at one point, and that makes me feel a lot better because I'm not just taking blind faith. I know exactly where this equation is coming from. So, as you can see, if you double this, let's say this is times 2, so if you multiply that times 2, it's going to be a factor of 4. So as you can see, the more length you have for moment, sure, it's going to affect the moment load quite a bit, but it's not going to affect the moment capacity. You're still going to have that moment capacity and shear capacity despite the span length. So that is a no as well. Your answer, as we thought and assumed before, was A. I really do hope I didn't confuse you with this. I was just trying to get a little bit more understanding because I could see how that D could be tricky. Don't be shy about going and underlining shear capacity. That's exactly actually what I did on the test. On my sample part of the test, I underlined shear capacity, so I knew exactly what I was looking for. Instead of shear capacity and not, shear design, you could even say shear design. Sure, that would be a correct answer as well, but it's not. It's simply shear capacity. All right, I will see you on question number 21.